So in the last video, we talked about left and right Riemann sums, which is where we take our region and we divide it into subintervals, and then we use either the left endpoint or the right endpoint of each subinterval to find the height of the rectangle, because it's the value of the function. Then we said, well, how can we make it more accurate? We talked about we could increase the number of rectangles, but maybe we sacrifice a little bit of efficiency. Another option is a midpoint Riemann sum. So a midpoint Riemann sum with most functions will have a little bit of overestimate and a little bit of underestimate, making them a little bit more accurate, okay? So with a midpoint Riemann sum, we are going to use the midpoint of each subinterval to find the value of the function to get the height of the rectangle. So let's look at this example. All right, so I posted a picture on my Instagram at 9 a.m. and then this table shows the number of hours since 9 a.m. and the rate P prime of t in people per hour that view my picture. Okay. The question says to use a midpoint Riemann sum with 3 subintervals to approximate the area between P prime of t and the t-axis from 0 to 12. Okay. And then we'll interpret that. So it does say to use 3 subintervals. Now, not all subintervals are equal. We're going from 0 to 12. If I wanted to break that into equal subintervals, then I would go from 0 to 4, from 4 to 8, and from 8 to 12. The problem is I don't have the midpoint values to do that. Okay, so I need to know, or I need to use just the numbers that are given because I don't have other information about what's happening. Okay, so this is what I'm looking for. I'm looking for a way to break the time frame from 0 to 12 hours into 3 subintervals, and I need to have the t value of the midpoint of each of those subintervals. Okay, so take a second and see if you can figure out how you would break it. Okay, so I see that I can go from 0 to 4 as my first subinterval, and I have a change in time of 4 hours, and the midpoint between 0 and 4 hours is 2 hours, and I do have the rate P prime at 2. So that's going to be my first subinterval. My second subinterval will go from 4 to 6, because I do know the value of P prime at 5, which is the midpoint. And the last one will go from 6 to 12, because I know the value of P prime of 9, which is the midpoint there. Okay, now, especially when we don't have equal subintervals and we have a table of values like this, which shows up a lot, what I like to do first is I put a label up above the graph of delta t just to show the width of each subinterval, because remember, the width of each subinterval is going to tell me the base of each rectangle. Okay, so I need to know that value. It is very easy to accidentally use the t coordinate rather than the width of the subinterval as one of the dimensions of your rectangle. Okay, so my first one goes from 0 to 4, so I have a width of 4. My second one goes from 4 to 6, so a width of 2. My last one goes from 6 to 12, so a width of 6. Okay, now I don't know what this graph is. I don't even need to try and graph it because I have all of the information I need in the table. I know that that area is going to be approximately, and then we have 3 rectangles. The first rectangle has a width of 4 and has a height of P prime of 2, the midpoint, and that is 30. Okay, so this is the width. So I'm going to say delta T1 times P prime of 2. Okay, plus, if I was labeling where those numbers came from, and then this one I have a width of 2, and the height of the function at the midpoint of that interval is 26. Okay, and then you can label that if you want. And then the last one goes from 6 to 12, so a width of 6, and has a height of 44. The height of that rectangle comes from the height of the value of P prime at the midpoint 9. Okay, so then I just need to evaluate this. So I get 120 plus 52 plus 240 plus 24 is 264. So this is 1, 2, 3, 410, 430, 432, 436. Okay, so 436 is my sum there. And I should, one second, I'm going to move that. Just because I want to be able to write under it. What are we doing here? Why is that flashing? Okay. So 436. And so then the second part of the question says, using correct units, interpret your answer in the context of the problem. So P prime of T is the rate of people per hour that are viewing the picture. If I accumulate a rate of change of people per hour, let's look at the units. So, oops. People per hour accumulated over some amount of hours, I end up with a total number of people. So what this is saying is that between, let's see, from time 0 to time 12. So from 9 a.m. to 9 p.m., approximately 436 people viewed the picture. Okay, so there's our interpretation. And it is an approximation because we used the Riemann sum. Okay, so that's a midpoint Riemann sum. And again, that's a little bit more accurate. If we go back and look at our original picture here, I'll use this one over here. If I were to have used a midpoint Riemann sum, well, actually, I'll just do it with one, even with one subinterval, I would have the area of this rectangle here, which would, again, still not be totally accurate, but it has a little bit of underestimate and a little bit of overestimate right here and a little bit of underestimate right here. So it's going to be more accurate than just a left or right Riemann sum by itself. Okay, so that's midpoint Riemann sums. Let's go and look at one more option. So this one is not specifically a Riemann sum because Riemann sum means rectangle, but it is another numeric approximation method. And this is called the trapezoidal rule. Okay, for a trapezoidal rule, we're going to be even a little bit more accurate than a left or right Riemann sum or midpoint Riemann sum because we are going to use two endpoints. We talked before. So here, I'm looking at the graph of sine x, and that's f1. It should just be like f sub 1 here. Get rid of that. Okay, but we're going to use a trapezoidal rule. So if I divide this into 4 equal subintervals, each one has a width of pi over 4. And if I'm using a trapezoidal rule, then I'm actually going to use both endpoints and turn it into a trapezoid and find the area of that. Now the height on the two ends is 0, so those are technically triangles, but that's okay. All right, so the idea here is I'm going to use the area of a trapezoid for each of these. Now, trapezoid is a tiny bit more complex than just a rectangle, so again, we're sacrificing a little bit of efficiency for accuracy, but we gain quite a bit of accuracy, okay? So for this one, the area is approximately, now because each one has a subinterval width of pi over 4, I'm just going to factor that to the front. So I'm going to say pi over 4 times, and then, okay, let's refresh one more time. The area of a trapezoid is the average of the bases times the height being the distance between the bases, okay? That height in this case is our subinterval, and I already factored that to the front, and that's the pi over 4. So now I just need to find the average of the bases for each of the 4 trapezoids. So for the first one, it's going to be, now I'm going to write this 2 different ways, first using function notation. So it's going to be f of 0 plus f of pi over 4, and then all of that's divided by 2, plus, actually, let me move this over. I'm cheating a little bit here. Okay, plus, next one, f of pi over 4 plus f of pi over 2, all over 2, okay, plus f of pi over 2 plus f of 3 pi over 4, all over 2, plus f of 3 pi over 4 plus f of pi all over 2, okay? Now, that would be writing with the function notation. That is not necessary. I just did that so we knew where everything came from when we look back at our notes. But really, what you do need to show, anytime you do this, calculator active or otherwise, you need to show the sum of the products or the values or the areas that you're adding together to get your approximation. So this would be the minimum step that would be necessary. So f of 0 is 0, f of pi over 4 is 1/2. So I'm going to do 0 plus 1/2 all over 2, and then 1/2 plus 1 all over 2, and then 1 plus 1/2 again all over 2, and then 1/2 plus 0 all over 2. Okay? All right, and then let's see. Just simplify this arithmetic a little bit. I'm going to take these 2's and factor them to the outside and make that a pi over 8. And so then I'm left with 0 plus just all the numerators added together. So 1/2 plus, so 1, 2, 3, 4. So that's a sum of 4 on the inside. So a total of pi over 2 is our approximate area. Okay? All right, one more example here. So here, again, we have a table. We do not have an equation, and we are showing the speed in miles per hour of a cyclist at various times. We are looking for a trapezoidal approximation with 6 subintervals to find the distance in miles that the cyclist traveled during the 12-minute time interval, okay? So 6 subintervals. First thing I'm going to do is count and figure out how many values I'm given. So if I use each of these, it's going to be 1, 2, 3, 4, 5. Yep, so I'm using all of them, okay? Another thing to double check in is for this type of problem is make sure that you're looking over the whole interval. It is the whole 0 to 12-minute interval, but sometimes you'll be given this and it might ask for like an approximation over the interval from 5 to 12 or something like that, and maybe you don't use all of the values. So please read the problem carefully. Okay, so again, first thing I want to do is I want to put the width on each of these because they are not the same, unlike this one up here where the width was pi over 4, so I factored that to the front. So I'm going to put my delta t on top, and so it's going to be 2, 3, 1. Oh, let me move those over. 3, 1, 3, 1, and 2. Okay, so my total distance, use a D here, is approximately, okay, and then my first trapezoid is going to be, now these are the, like this is base 1, base 2, base 2, base 3, base 3, base 4, etc. Or we could say 0, 1, doesn't matter, but these are the bases that I'm adding together. So 33 plus 25 over 2, that's multiplied by 2, plus, and then the next one I'm going from 2 to 5, so 25 plus 27 over 2 times 3, plus 27 plus 13 over 2 times 1, plus 13 plus 21 over 2 times 3, that's this subinterval right here, plus, and I did it again, oops. Let's see, I just did from 6 to 9, so from 9 to 10, so 21 plus 5 over 2 times 1, plus, and last one, 5 plus 9 over 2 times 2. Okay. All right, then I just have a bunch of arithmetic to do. So once again, you have to, and actually I think this is what, yep, this box right here says, if you are using a Riemann sum or a trapezoidal rule, you have to show the sum of the products, okay? Calculator or not, you have to show the sum of the products to make sure that you are getting the full points here, okay? And where it says don't perform any arithmetic calculation, that I haven't done it. Like I didn't do 58 over 2. I just wrote it as 33 plus 25, okay? All right, so I'm gonna go ahead and add these together. So actually that's gonna be, cancel those out. So 33 plus 25. So I've got 58, and then, so this is 52 over 2 is 26 times 3, which is 78, plus here I've got 40 over 2 times 1, so that's a 20, plus 34 over 2, so 17 times 3 is 51, plus 26 over 2 times 1 is 13, plus 14. Okay, so still doing more arithmetic. Let's see. 5, 12, 13, 14, 15, 16, so 21. Plus, so 210, and then 16, 17, 18, 19, 20, 24. So 234. Okay, what does this represent? This is 234 miles is the approximate distance traveled by the cyclist. Okay, so where we're going next. So this is kind of 6.1 and 6.2. 6.2 is really the part about the Riemann sums, like the specific use a left Riemann sum, right Riemann sum, etc. But where we're going with this is we do need to know the approximations, but the next question then is, how do we make this exact? Okay, so how do we not just have an approximate area? How do we have an exact area? Okay, so let's go back up to this graph for a second. This one we started with at the beginning. Get rid of all this, okay? And so if I want to know the exact area here, and I do this by dividing into rectangles, the question that we ask is, how many rectangles do we need for this to be an exact area? The answer is an infinite number of rectangles, okay? So that's where we're going next, is we're going to say, how do we have an infinite number of rectangles, and then the area of each of those rectangles, and then add all of those together. In other words, an infinite sum, okay? And because we did chapter 1, we know where this comes from. We know that that means that if we want an infinite number of rectangles in here, so an infinite number of subintervals, we are going to use a limit where the number of rectangles or the number of subintervals is going to approach infinity.